China in Beijing, and then went to Stanford, where he got his PhD, and then to Berkeley. And Stanford, among other people, he worked with former Santa Barbara scientist Mike McGee. Berkeley, he's collaborating with Aaron Majumdar, and he's in a group with Paul Olivasatos there. It's been about 2 years now at Berkeley, and it's accomplished an incredible amount of things. So it's fun to talk to him about many things using nanostructures in the field of energy devices. And among other things that he'll tell us about today, very recent work where they are making thermal rectifiers that will let heat pass more readily in one direction than another. And quite an amazing record of things that he's done. We're just so pleased that you can come and tell us about your work.
Great, great. Thank you very much, Art. Thank you for the invitation, and I really appreciate the chance to talk to you what I've done. In the past few years, my research has been primarily focused on at the intersection of energy science and nanotechnologies. So today, the talk is about both of them. I try to use nanostructures for energy applications, basically. So also in the past few years, as Art mentioned, I have a great fortune to work with a lot of great mentors and collaborators. You will see their names popping up along the way. So I don't think I need to work that hard to motivate this audience. Just a few quick overviews. So everyone knows energy is grand challenging of our time. What we're doing now is that we're burning fossil fuels to generate heat and using heat to produce electricities. And then we distribute electricity to building industry. And now we're trying to electrify the transportations. And sometimes people forget, especially during the rainy days, the sun is the ultimate energy resources, right? It just takes millions of years for them to convert the energies into fossil fuels. So the problem we have now is that we're using a lot of energies. In 2008, the global energy consumption is 15 terawatts, and we're about to double the number in 2050. So what can we do? Well, we can go back and burn more fossil fuels, and we will burn more fossil fuels in the next couple of decades. But what else can we do? I think the key lies in the three things: the sun, the heat, and the electricities. Not just that they're cleaner, but also they provide a buffer layer for better storage and distributions. So today the talk is really about the three things: the heat, the sun, and the electricities. Or fundamentally, it's really about those three energy carriers: phonons, electrons, photons. If you can control the behaviors of these three energy carriers, you can innovate energy devices. And because of the unique length scales, you can really use nanomaterials to control the behaviors of these energy carriers. There is a famous saying that there are two kinds of science, physics and STEM collections. Right? I agree with that, and I think they deserve equal respect. So the story I want to share with you today, and the message I want to deliver, is that when you can control the materials at the nanoscales, then you can tailor their properties to examine, to reveal the fundamental complexity, to probe the fundamental properties, and you can tailor the properties to control the behaviors of phonons, electrons, and photons, and to innovate energy devices. There are two parts of it: fundamental understanding and energy applications. I'll also let these images to whet your appetite for what to come. The first story is about heat. 90% of world's energy utilization is going through heat. So it's all pervasive. It's there whether you like it or not, right? For example, as you might notice, computer is getting hot. So hot that you can make egg out of it. It's not that PC attacking Mac. It's something more fundamental. It's something more fundamental than that. Why is it so hot? You know, we enjoy cheaper, lighter, and fast computers because we do scaling laws. But as we compact more functionalities into smaller areas, energy density dramatically boosted. If you look at the numbers is standing around 100 watt per centimeter squares. So that's equivalent to nuclear reactors. So we're holding lots of that energies in the computers. To make things even worse, as materials scales down, the phonons run into boundaries more often, so that the thermal conductivity gets dramatically reduced. If you compare 10 nanometer silicons, the thermal conductivity is orders of magnitude smaller compared to the bulk values. So you put in a lot of heat, you put a lot of energies into the computers, and it's hard to get them out, right? So that's why it's getting so hot. So what are the solutions? Well, typically we use fans, right? So this image is trying to deliver a message saying that in the past couple of decades, we made tremendous progress in the electronic layers. But compared to that, not much has advanced in the thermal part. Can we learn from what we got in the electronic layers to improve the thermal part? Second, a lot of electricity eventually become heat because of Ohm's laws, right? And what we're doing now that we're consuming more electricity to fight against this heat. Because, for example, fans are consuming electricity. We use that to fight against heat flows. Can we do something better than that? Because it's very important. If you look at the big pictures, this is the US energy consumptions. This is a study performed at the LBL. Big chunk of that is consuming the buildings. And there are two kinds of buildings. In the residential buildings, 40% of that is just for cooling and heatings. And not much better in the commercial buildings. 30% of that is for cooling and heatings. It's because we don't have very good control about heat. We're constantly consuming other forms of energies just to fight against heat flows. So can we do something better than that? In principle, we can't, because electronic and thermal areas are following basically the same laws. If we apply a potential difference across materials, there will be current passing through, and the ratio between them is resistance, right? This is Ohm's law. And if you apply a temperature difference across same materials, there will be a thermal power passing through, and the potential between that is the thermal resistance. So essentially the same law under different names. But look at what happened to the electronic devices. Totally revolutionized every aspect of our lives. But the thermal part still remain in the regime of Fourier's law. So is there anything we can do about it? Don't get me wrong. We're not trying to build a thermal computer to compete against the electronic computers. Essentially, we're trying to take thermal heat as energy carriers. If we can use electronic devices to control electricity, can we build a thermal device to control heat? That's a goal. Is to develop advanced thermal devices to self-control the heat flows so that we don't use other forms of energies to fight against it. All the cornerstone for electronic devices is diode, right? Let's start with the basic functions, diode. Can we build a thermal diode, right? What do I mean by thermal diode? Well, if you flip the direction of the temperature gradient, you found the heat flow going the other way. This red P will be different from the black P. That means there's diode there, right? Is there a diode experimentally? Yes, before us, Alex Zettel group, UC Berkeley, they demonstrated that experimentally in 2006. They found if you have a carbon nanotube or boron nitride nanotubes and it deposits some carbon composite on one end, you accidentally find that there is rectifications. The figure of Mary is defined like this. The high value of thermal conductance minus smaller value over the smaller values. And they found 7% differences for boron nitride nanotubes and 2% for carbon nanotubes. So it's a beautiful works, and they claim it's the first thermal diode. But of course, there are a lot of things can be done. And I got my PhD in WE Stanford, and when I moved to Berkeley and started to look at these problems, I thought I'd find a gold mine, right? At this era of you can build tons of millions of transistors, you're looking at essentially a pre-transistor era in the thermal field. So I thought I'd find a gold mine. So I think, why don't we just build a thermal analog of everything we have in the electronic devices? But it turns out to be very difficult, both fundamentally and technically. So let me explain to you the story. Why it's so hard to build a thermal diode? Well, first, for most of dielectrics or semiconductors, the heat carriers are phonons. Those are the quantity of lattice vibration, right? So first of all, phonon has 0 chemical potentials. The way you build an electronic diode, you have 2 electrons with different chemical potentials. One p-type and n-type, you put in one go uphill, one go downhill. So that can build an electronic diode of that. But you cannot do that for the phonons. Second, phonon has broadband and has much smaller coherent length compared to photons. So in like a photonic crystal, in the optical community, people try to build photonic crystal to control the behaviors of photons. But it's very hard, especially experimentally, to build that for the phonons. It's very hard. So how do we make a diode? Well, if you think you know electron enough, you have better control in electrons. Perhaps you can use electron to help. There's one proposal that attracted my attention. This is a paper published in 2011. So they said if you have a metal put together next to insulators, something amazing could happen. Because in the metal, the major heat carriers are electrons. And in the insulators, major heat carriers are phonons. In order to do the heat transfer, you need to, those two things actually cannot talk directly to each other. They need to rely on phonons in the metal to do the communication. So if you want to transfer energy from metal to insulators, electrons give their energies to phonons in metal, and then 2 phonons talk. If you want to, for example, insulator is hotter than metals, the 2 phonons talk together first, and then phonons give the energy to electrons. So it's a 2-step process: electron-phonon coupling and phonon-phonon couplings. I just explained to you, phonon-phonon coupling cannot be a diode, so it's become a thermal resistance, right? But electron-phonon coupling, you need to follow Fermi's golden rule. You need to, if the electron give the energy to phonons, emit phonons, they go downstairs. So if they absorb phonons, they go upstairs. It turns out it's easier for them to go upstairs because there are more available states there, right? So that's where the asymmetry comes from. It's easier to transfer energy from phonons to electrons. So that can be a diode. But then people ask why it's so hard, right? You have a metal, you have an insulator, you should get a diode. If you look at this, the answer is pretty clear because you have a diode, but it's connecting to a resistance. If resistance is big, you don't see a diode, you see a resistance behaviors. So you want to minimize the resistance due to phonon-phonon coupling in order to see a diode. How do we do that? Well, in my mind, at least there are 2 requirements. Because first, phonon is like a lattice vibration, quantum of lattice vibration. The vibration of one atom need to efficiently enable the vibration of the other atoms, right? In order to efficiently reduce the resistance. So you need to have very strong bond and perfect interface to do that. Second, phonon is like photons. When they hit the interface, they like to reflection. They like to be reflected. So in order to minimize reflections, you want to provide acoustic impedance match. That means the metal and insulator need to be built based on similar material systems in order to reduce the reflections. So that's why we choose to use vanadium dioxide material systems. So it's beautiful systems. Some of you working in the materials know. You have both metallic phase and insulating phase. And there are only slightly structure change along these directions, 1% change structurally between these 2 phases. And there is plenty of ways to make metallic phase and insulating phase within a single nanostructures. For example, in the literature, people have reported starting with vanadium dioxide beams, you start to bend it, right? Because originally it's insulating phase at room temperature. It start bending, start to increase the stress. And then there's a metallic phase popping up. The beauty of this material system is that the different phases has different reflections because metallic phase tend to be more lossy, so look darker. So you can just look at them under optical microscope, and also, of course, you can examine using Raman and all other systems. But it's a convenient way to look at under optical microscope to see where the metallic phase is popping up. In this case, it's popping up where the stress is building up. There is other ways. For example, if they have this single crystal VO2 beams, right? And you heat it up, these 2 ends are clamped together. And once it's reaching the phase transition temperature, there is a 1% lattice shrinkage, right? So that you simultaneously change the temperature and the stress. So we're following along this line so that you can see there's metal insulated interface across a large temperature range. So also people find if you change the stoichiometry, for example, you start with VO2 and then you treat it under hydrogen reduction environment, you can have stoichiometric variations in metallic insulating phases within these single nanobeams. So there are plenty of ways. In our study, we found the easiest way is that to start with tapered nanobeams. The beauty about that is that at the regime where the diameter changes, there are also these defect roughnesses. You can relieve these lattice transitions so that you can pinch the metal insulating interfaces right there. And once you heat up to certain temperatures, everything becomes metallic. So we decided to use that. The synthesis part is actually pretty simple. You put it in the VO2 powders, and you carry it by the carrier gas, and you collect everything downstreams. And you choose certain catalysts to control the size. And you can get uniform sizes and taper shapes, depends on the growth conditions. And you can always track whether it's VO2 or not by doing electrical transport. You found the phase transition is always happening at 340 Ks. And we choose these tapered wires, right? We tried a lot of them, and every single time, electronically, it behaves very much the same as uniform wires. You see a beautiful phase transitions at 340 Ks. So we decided to do the measurement. Many of you have known that the thermal measurement is not as straightforward as somebody expected. So this platform is actually developed by my collaborators at Berkeley Aruma Junda Group. This is a very powerful technique. I can go into details in a few minutes. Essentially, it's a platinum coils sitting on silicon nitride island. There are two islands, so you get the same. The nice thing about this platinum coil is that once you can put current in and heat things up. You can serve as a heater. At the same time, you can do this 4-point probe measurement to accurately measure the electrical conductance, which has a temperature dependence, right? So that you can serve as a sensor. So you heat things up, and you know how much passing through, and you know the temperature differences, and you can go back and track the thermal conductance. Of course, you can also measure the voltage differences. You go back and track the thermal powers. And you can make 4-point probe measurement on the single wires to track the electrical resistance. So it's a powerful platform to extract the electrical conductance, thermal conductance, and thermal power at the same time. So give you a clear idea. It's now become standard for single nanowire thermal transport measurement. But in our cases, the requirements is even strict because thermal measurement, it's already pretty tough to get the order of magnitude right. But we're only talking about a few % differences. Want to make sure it is right. Also, we want to measure across a large temperature differences. So that we run into a lot of troubles. And just share one or two with you. For example, the black backbone of this whole setup, as I said, is this platinum resistant thermometers. And it has this nice linear temperature dependence of resistance. So, and this slope is very sensitive, right? So that you need to carefully calibrate it. But when you do a large temperature range scanning, you find that it's no longer linear. So that we run into lots of troubles because the final result is very sensitive to the slope of these curves. You need to very carefully study that. So one solution is that we're adding more sampling points. And but then the thing is that, for example, if you do a small step, we're only doing 2K step in order to carefully sampling the whole slopes of the curves. You need to have very fine temperature control. And it takes a very long time to everything to be stabilized at certain temperatures. So as you will show, each curve takes about 2 weeks to do the full temperature scannings. And then you carefully choose the local slopes in order to carefully calibrate that. So there are a lot of headaches we're running into, but we're being very careful in each step. So this is one of the examples. It's tapered wires, and zooming pictures. The thin end is 950 nanometers, and the thick end is about 1.5 microns. And length is about 10 microns. It can be shorter, like 1 to 2 microns. And you see, this is a Q versus delta T curve. Essentially, it's IV curve, thermal IV curves, right? So the slope of this tell you the thermal conductance. You found that if you change the directions of temperature differences, you see the slope is different. This is at 300 Ks. You find that there is a 22% differences observed. That means thermal coefficients is about 22%. And once you heat it up above 340 K, this is 350 K, you see the slope become the same. So the rectification is below 1%. So this is pretty exciting. And we have measured a couple of tens of devices, and its rectification is always there, and it's disappeared above 340 Ks. So the device performance is very consistent. And there is no rectification showing in the uniform beams. We're doing very careful control to show that. So this is a key piece of data. It's also a little bit complicated. Let me walk through that with you. So this is temperature dependence. This is temperature versus the thermal conductance measurement. You find we're ramping from very low, 50 K, all the way up to 380 Ks. And you found at a low temperature is following traditional semiconductor behaviors, because at a very low temperature, phonons run into the boundaries more often, so the thermal conductivity decreases. And at this region is phonon-phonon scattering dominated, because at high temperature start to populate more phonons, and the phonon-phonon coupling become dominant mechanisms. And the peak values is always impurity scattering dominated, right? So it depends how high the thermal conductivity can go. So this is a red curve. It represents thermal conductance along these directions. And you measure, and once it hit above 320 Ks, everything starts to increase, because now it becomes metallic phase. So electrons start to contribute. So thermal conductivity increases once it crosses the transition temperatures. So, and if you plot the green curve, you find this is a thermal conductance along the other directions. The trend is largely the same. And the two curves converges at low temperature and high temperatures. But there's a significant differences around these regions. And we estimate the error bar by the most conservative ways. This is a 4% error bars, and we find rectification is still there. So we plot this. This is rectification numbers represented by here. So you see it's 22% even with largest error bar. It's always there. And disappeared at lower temperature and high temperatures. So now it's perfect, right? We have metal insulator interfaces, and we see rectifications. Works as we expected. But there are two things that bothers me all the time, because, for example, if we examine the same devices, right, and you put them under optical microscope, and you found metal insulator interface does exist, but it exists at a very narrow temperature regime. It's only exists between 65 and 68 degrees C. And the reason for that is pretty simple, because now this wire is sitting on the two islands, right? They're free to move, essentially. If it's a fully clamped structures, as shown before, the metal insulator interface can exist all the way across a larger temperature range. But if it's freestanding wires, it's just across the transition temperature, and it's going to the metallic phase, right? In this case, it's somewhere in between, but more close to the freestanding cases. So it only exists for very narrow temperature range.
So what's the interface?
Oh, sorry. So it's probably more obvious in the North California. It's here. You see, this one is darker than this one. You can see, right? And here, this region is darker than this region. Yeah. So the interface is pinched right at where the transition happens. So this is one problem. This interface region 67 degrees C is where thermal conductance we observe rectification already disappeared. So it happens at a region we don't see rectifications. That's the problem. Second problem is that when you run a little bit of calculation, and you calculate the resistance due to electron-phonon coupling, and you find that it's about 1 gigawatt per meter square K. That's a good thing. That means electron-phonon coupling can be a dominant part for the interfaces. But remember, there are two other parts, because VO2, bulk thermal resistance, also is there. So there are two thermal resistors connected in series. And if you run a number and you compare to the value you got experimentally, you found just one interface is not enough to make it a dominant part for the whole thing. So that means interface we see cannot be the reason to explain the thermal efficiency. So what's really going on here? So we dig into that, spend a lot of time on this, and we think we find some clues, but not completely. One thing is that we calibrate the thing and compare with uniform wires using OJ electron spectrum. And what we found is give you an accurate number about stoichiometries. And in the uniform wires, you found it is also surface sensitive techniques, right? And you found that oxygen percentage is about 71, 72% on the surfaces. This is understandable because it's VO2, but environment is oxygen rich, right? So it tends to be oxygen rich surfaces. Give you an idea, VO2 is 66.7 and V2O5 is 67%. So you have oxygen-rich surfaces. But in the taper-shaped wires, which categorize that, we found even in oxygen-rich environment, the surface is still oxygen deficient. So it's below 66.7%, and you have a much larger variations. What does that tell you? Well, if you look at dig into the literatures, and you found all the phase transition for the VOX family, you find that the transition temperature is very sensitive to the stoichiometries. For example, this is a V2O3, and this is a V2O4, essentially VO2, right? A little bit variation in the stoichiometries can have a huge change in terms of phase transitions. For V2O3, it's about 170, and for VO2s, it's around 40 Ks. So that means if stoichiometry is get messed up, there are lots of metal petals existing in that films at certain temperature regions. So I think the physical picture is like this. At the temperature region, where there's a metallic petal due to the stoichiometry variations, we see the thermal activations because there are multiple metal insulating interfaces right there. And phase transition actually help to erase all these metallic petals, make it the uniform phases at high temperature and lower temperatures so that you don't see rectifications. That's also very interesting because electrically they behave exactly the same as uniform wires. That means you cannot use electrical method to probe that, but thermal method is more sensitive to these small little features. That's actually very important. Now you can use thermal method to probe the material properties. Also, application-wise, is also very important because we see thermal rectifiers, and it's up to 22% rectifications, and this is highly ever observed. And even more exciting is that you can use temperature to get it to tune these thermal rectifications. At low temperature, it's a diode, and at high temperature, it's a resistor. It disappeared. Of course, the technology is still in its infancy, but we can clearly envision some potential applications because essentially two states can function differently. At a lower temperature, it's diode, so you can use that to hold your heat. At high temperature, it's a resistor, so you can efficiently dissipate that. What are the applications? Well, for example, coffees, right? We drink it every day. And actually, some physicists did some research very carefully. When it's freshly brewed, coffee is 85 degrees Celsius. You don't want to drink it at the time. So you want to cool down very efficiently. But once it down to your comfortable zones, you don't want to go down further, right? So you want to heat it. So it can enable the pass efficiently and hold the heat whenever you want it. But people say, well, I don't want to be 68 degrees Celsius. Choose some other temperatures. Well, it turns out if you can, for example, in VO2 systems, you can add in a little bit of tungsten. You can tune the phase transition linearly by linearly adding the tungsten compositions. In general, actually, it's very important because we do certain things at certain temperatures, but the general environment is always volatile, right? So it can be applied to different kind of things. For example, buildings we consume lots of energy in buildings. But if we can use this kind of techniques, if we want to hold the heat, we want to keep it warm, then we turn on the devices, hold the heat. We want it to be cool, we turn it off, right? For the solar thermal storages, you want to store it, we turn it on. And you want to release use it, we turn it off. So, but of course, a lot of things need to be done down the road in order to enable many applications, like rectification, numbers, lifetime scalability, cost integrations, other things. But I think it's important first step. So this is the first part of my talk. Is about the temperature-gated or switchable thermal rectifiers for self-control thermal devices. Second part is about photovoltaics, how to convert energies from the sun into electricity. As everyone knows, it's a photovoltaics, right? It's a device everybody is familiar with. Just to keep everyone on the same page, it's a diode, electronic diode. So if there's no light, it's a diode behaviors, right? It's we call it dark current. And once it should light on, it become like this. So the maximum voltage you get is here. We call it open circuit voltage. And maximum current got here is here. It's called short circuit current. And you cannot get both of them at the same time. So maximum power you can get is here. And the field factor is defined by this maximum power over GSC times VOC. And the efficiency is maximum power you get out of this over the input. And good number to remember is that according to standard solar spectrum and 1.5G, solar energy density is about 100 milliwatt per centimeter squares. So it's a very good number to remember. And a lot of things has been happening in the field. This is some of the major players, right? And this is, I think, data from 2010, but it's already out of date because a lot of things have happening in OPV systems, and people are trying to make a gallium nitride multiple junctions to even boost the efficiencies, and people try to make all kinds of material systems to do that. But let's think about it. What's the ultimate goal, right? Ultimate goal, I think we buy solar cells to essentially buy electricity. So ultimate figure of merit is $ per kilowatt hours, right? So in terms of that, ultimate goal essentially is high efficiency, low cost, and long lifetime, right? So we want to capture all the light and collect all the carriers to enable high efficiency. We want to use cheap materials and cheap processes to reduce cost, and want to last forever, right? Like diamond. 25 years is actually industry warranty for the lifetimes. So it's, of course, very challenging to get these perfect solar cells. But in my opinion, all the challenges are fundamentally related to two length scales. First is absorption depth. How much does it take to absorb all the light, right? For low cost, you want to use as little as possible, as thin as possible. But for high efficiency, you want to be thick enough to capture all the light. Second length scale is so-called diffusion length. To enable high efficiency, you want to carriers to travel long enough before recombination happens, right? But let's face it, typically lower cost process give you a little bit lower quality material systems, meaning shorter diffusion length. So fundamentally, problems due to the mismatch of these two length scales. How do we solve that? There's a lot of strategies to go through that. But if we can efficiently reduce absorption depth, then we can use much thinner material systems. So that even when the material system is lower quality, the shorter diffusion length is shorter, you can still enable efficient carrier collections. So that's what we call photon management or light trapping. Light come in, we want to minimize reflections and transmissions. We want light to be trapped within these thin materials. So suppress reflection and enhance absorption. And light trapping for solar cells is essentially three functions. You need to have broadband because solar spectrum is broadband. Second, the process involved must be scalable, right? Because we're talking about terawatt scale applications. And also, at the end of the day, next generation solar cells want only a couple hundred nanometers to absorb all the light. So all the things need to work at sub-wavelength region. So when I was at Stanford, in the lab, we're developing these processes. We synthesize silicon dioxide nanoparticles with uniform sizes, and then we assemble them on top of semiconductors, close packed. And we use that as an etch mask to get these nanostructures, nanowires or nanocones. What do I mean by nanocones? The diameter of these structures gradually change from roots to tips, as you will see in the SEM images a few slides later. So the roots is about a couple hundred nanometers, and tips only a few nanometers. So it can be done at a very large scales. This is 4-inch wafers. We can do even larger than that. And this is the SEM images. The diameters and the spacings and the lengths can be controlled independently across a wide range. And let's use amorphous silicon as an example to demonstrate the effect. Amorphous silicon is one of the most important solar cell technologies. And it certainly has advantages. It's silicon, everybody like silicon. And it's abundant, non-toxic, and huge infrastructures. Second, it's amorphous. It can be deposited at low temperature on flexible substrate through rotary processes. And it has much better absorptions compared to crystal silicon. Crystal silicon is indoor bandgap materials. It takes a couple hundred microns for absorption. But for amorphous silicon, it's about 1 micron absorption depth. But the problem for amorphous silicon is that the efficiency is relatively low. If you make a triple junction, use silicon germanium, right? And you get 30%. Now it's a little bit higher than that in the lab. But if you buy them from the market, it's about 5 to 8%. The problems behind that, first, there's a so-called Stepler-Wronski effect. If you put those things under the sun for a couple of hours, the performance starts to degrade. And after 10 to 30% degradation, stabilize it. And people find if the film is thinner, the degradation won't be that much. So thinner is better. Second, there's absorption collection trade-off. We talk about absorption depth is about 1 micron, but the carriers can only travel about a few hundred nanometers at most. So there's a trade-off between absorptions and collections. That makes light trapping very desirable for amorphous silicons. Let's look at the reflection first. Reflection happens whenever light hits interfaces. A simple calculation, if you use amorphous silicon, if you don't do anything, 36% of light will be reflected right away in the first places. So industry is use a quarter wavelength transparent oxide to induce the destructive interference to suppress reflections. But as you can see from this term, it's really a narrow band effect. It will be more desirable to form this graded refractive index. So the light come in will not hit the interface, so that you confuse light get coupled in with much reduced reflections. So how do we do that? Well, if you calculate the effective refractive index weighted by volumes, because this gradual change of the nanocone diameters from a few nanometers to a couple hundred nanometers, the refractive index actually gradually change from air to silicons. So I need to remind you, this picture only applied when those geometries are deep subwavelength region, so that light don't see a wall. You can confuse light that way. So one simple experiment we try. We start with 3 samples, exactly the same, 1 micron amorphous silicons, and then convert one of them to wires, one of them to cones, and that's what it look like. For the thin film, it's mirror-like, right? Because light come in, get reflected, you see a lot of reflections. And the cones become black because light come in, do not get reflected, and it get absorbed. And then wires somewhere in between. And we did even quantitative measurement. This is a wavelength scanning. Above the band gap of amorphous silicons, cone is always better than wires, which is better than thin films. That's good. It's a broadband effect. It's always maintaining above 90%. And it's even more amazing is that it has a wider angle of incidence effect. Above angle of incidence, I think 30 degrees, light, its reflection is already gets suppressed in the nanocone cases, and thin film cases is the worst part. So, but in these cases, we're using 1 micron thick amorphous silicon. We think it's too thick, and we're etching directly on amorphous silicon, which can cause lots of surface damages, and we don't want that. So next experiment we try, instead of making amorphous silicon cones, we make cones on quartz or glass substrates. So it also will reduce the aspect ratios to reduce the surface areas. So this is a SM images. This is a cone, but with much reduced aspect ratios. And we can control the periodicities by controlling particle size. And then we deposit standard single junction amorph silicon films. And that's what I look at afterwards. So all the pattern get transferred to the top layers. And the periodicity maintain the same. And to do the comparison, we did that exact same batch. We're putting in a thin film, and we'll do the comparison. Optically, nano cone is better. In this case, it's more like a dome. We call it dome, whatever. So it's better than thin films. Overall perception about band gap is 94% versus 65%. To understand what's really going on here, we build exactly a model optically and shoot light from the top, and then we try to see what's exactly happening. So you see, at the shorter wavelength regime, semiconductor is very good absorbers. Once light come in, it gets absorbed right away. So from the simulation data, this white, big contrast colors meaning there is light. Once it becomes white, it means all the light has been absorbed, right? So for the short wavelength regime, once light gets coupled in, get absorbed right away. So the difference you see here in the short wavelength regime is due to reflections. That means even the cone becomes slightly like a dome shape. They still maintain a good anti-reflection properties. And once you move to the longer wavelengths, things become even more interesting. Because in the thin film case, you see peak and valleys. That's due to the Fabry-Perot interference, right? Light come in and do not get absorbed and come up again, start to interfere with reflected light in the first places. So it's Fabry-Perot interference. But that interference gets gradually suppressed in the nanodome cases. So what's really going on here? You see, for example, at 700 nanometer wavelength regimes, you not only see a beautiful EX component, you also see a EZ component. That really means light coming get coupled into the guided mode. So start to travel along these directions. So light path lengths get dramatically increased and absorption get dramatically enhanced. So we make devices out of it and then we test it. A short circuit current in these nanodome cases is 17.5 milliamp per centimeter squares, which is a lot higher than our control devices. And this is very good numbers to give you an idea. The theoretical single junction short circuit current calculation is 20.5 milliamp per centimeter squares. So it's very approaching the numbers. And overall efficiency is also much better. It's about 25% higher than the control devices. So pretty much at the same time, slightly later, Harry et al. Group essentially demonstrated the same thing, but used thinner films, but they achieve a little bit lower short circuit current. And recently, collaborating with a European group, we got an even boost efficiencies. Now we achieved 10.9% efficiencies, which is on the bar of the world record efficiency. That's actually a good thing, because traditional wisdom is that for light trapping, people know there's a Eli-Yablanovic limit, saying random structure is best for light trapping. That's true in the geometric optics, but people never know whether it's true in the nanophotonics, in the wave optics. So in this case, we experimentally demonstrate that through periodical patterning, we can achieve efficiency higher or on the par of these random textured surfaces. And now our collaborators at Stanford also prove that theoretically, the random structure is not the best for the light trapping at the nanoscales. So people are clear about this part now. So let's do a little summary here. Nanocone solar cells, it has a broadband anti-reflection properties, so it can couple light in with much reduced reflections. And for this longer wavelength light, it can couple that into the guided mode and to increase light optical length, path length, and enhance absorptions. And because of that, we can reduce the thickness and to enable efficient carrier collections. And do everything through scalable processes. And we think it can be applied to different kinds of solar cells, because we didn't change the solar cell structures above, right? We're actually working with different collaborators worldwide, try to generalize this concept. We think we can use that to improve efficiency because we can reduce optical loss, electrical losses, and we can reduce material usage, improve the throughput. And for cadmium telluride and CIGS, there's not enough indium and tellurium on Earth to support terrestrial applications. You can minimize the material usages. You can fundamentally increase their scalabilities. So we do think it can be applied to different kinds of solar cells. Give you quickly an update on another project. This is a collaboration with the Mike McKee group and Mike Grasser group. We're applying these nanostructures to solid-state dye-sintized solar cells. Essentially, we're doing imprinting processes to make these nanocomb patterns, and we feel the rest of processes as the same as a standard solid-state dye-sintized solar cells. And we found that there's boost in the short-circuit current again, and all the improvement is in the longer wavelengths where you need the absorption enhancement. And this 6% efficiency is again on the par of the world record, highest achieved in solid-state dye-sintized solar cells. So lots of things still going on right now. So what I have demonstrated is two types of nanostructures enable two kinds of energy devices. So what are the other opportunities? So let me quickly share with you. So in the nanostructure or nanowire community, there is a well-known mechanism to grow these nanostructures called VRS growth. Right? You start with a metallic ball and you heat it up to a eutectic point and bring in the precursors and form this supersaturation regime. For example, if you want to grow silicon, you bring in silane and you nucleate one-dimensional growth. And one thing we tried in the early stage of my PhD that we see how about we keep fitting the catalyst. Will that branch out? So material system we use is less selenide. It's rock salt structures, very simple process structures. And we did see what we expected. First is the one-dimensional wires. Once you keep fitting catalyst, start to branch out, and a lot bit more time it can go crazily. And it's all epitaxial because you see all the directions are vertical to each other, as single crystals, carefully examined by TM. And it can go multiple generations and become a forest. And pretty quickly we'll find something even more interesting, that if we tune the diameter slightly, we found there is something. Anybody has questions? No? So we find something even more interesting, is that this is a high branch structure we talk about. And this is something completely different. You see there's main wires, and there's secondary wires twist along these directions. So we call it chiral branch structures. You see this is a main wires, and there's two pairs of secondary wires, and they're rotating along these main wires, right? It can be beautiful, crazy. But we want to understand what's really going on here. So if you dig down into literature, you found in 1959, people actually proposed that the screw dislocation can drive the one-dimensional growth. What do we mean by screw dislocation? Right? For people who don't know, if it's a perfect crystal, you start with one side, it goes through 160 degrees C, you back to your original point, right? But if there is a screw dislocation, you start from here, it goes through 160 degrees, you find you're one step higher. And that step is Brooks vectors, categorized by Brooks vectors. That means there is a screw dislocation there. The nice thing about this is that they always have this active site to accumulate the atoms. Atoms tend to be accumulated here, so they can facilitate this one-dimensional growth, right? It's actually proposed 5 years earlier than this VRS growth mechanisms, but people later on forget about this or doing this. And even more interesting is that a physicist, John Ashby, in 1953, he predicted if there is a rods and there is a screw dislocation within the rods, in order to be energetically stable, they tend to twist itself. So the periodicity of this twisting is proportional to r squared, which is a radius, right? And over Brooks vectors. So one nice thing about our structures is that if the rod twists itself, you won't be able to see it. Only when there is a secondary branch come out and twisting along this self-twisting, you'll be able to visualize these twistings. So this is the first visualization of Ashby twist. Then people ask, why nanostructures, right? You see the Brooks vectors is always close to the lattice constant, about 1 nanometers. So if R is large, it's micron scales, the L will be very large. So the aspect ratio will be huge, will make it impossible to see this twisting. It's only when R is close to Brooks vector, which is a nanometer region, you will be able to see these twistings. So then we do careful study. You go back and you measure the periodicities by judging by these secondary branches. You carefully measure diameters and then go back to extract the Brooks vectors. They're once or twice of lattice constant, which matches well with the theory. And also a careful TM experiment, you will see if you do the dark two beam condition images, and you see you can tune the diffraction vectors to make the screw distribution line showing up and disappear, and using that to judge the Brooks vectors, which is all one directions, which makes sense. And but then people ask, well, okay, now we understand it. How do we go one step further, right? How do we do this in a more controllable way? Well, in order to control the screw dislocation growth, there are two things. First, how do we nucleate these dislocations, right? How do we create a dislocation in the first place? Second, once we have that, how do we facilitate this growth mode versus the other growth mechanisms? So it turns out how to create a dislocation in the first place is either part. You can intentionally using silicon wafers but with intentional miscut. So you have these atom steps for you to nucleate that. That combined with a lattice mismatch between silicon and lacilonide can efficiently generate dislocations. And then how do we facilitate the dislocation growth models? Well, according to the traditional BCF series, dislocation-driven growth, layer by layer growth, and dendritic growth progressively dominant as you increase the supersaturation. Of course, there are small overlaps here. This is where you see the mixed phases of. But if you intentionally reduce the supersaturation, then you will start to make the dislocation become a dominant growth mechanism. So combine these two, we are able to grow this screw dislocation-driven nanostructures, chiral branch structures in a large scales. So a summary for this part, these chiral branch structures, the main structures is driven by screw dislocations. The secondary branches is driven by catalysts, it's still VOS growth. And interesting thing is that almost at the same time, another group find the exact same thing in a similar material systems. In our case, it's less selenide. They find it in the less sulfide systems. And because these two papers generate lots of interest in community, later on people report screw dislocation-driven growth in the zinc oxide systems, in the nitride systems, like gallium nitride systems. And people in rice actually claim that can be used to explain the carbon nanotube growth. Essentially, different karyotes explain different Brooks vectors. So it now become a generalized growth mechanism to explain catalyst-free nanowire growth mechanisms. So what are the opportunities? Well, lacilonide is actually very interesting materials for solar cells, as some of you might know. And those hyperbranch structures actually is perfect because it decouples upstream depths with diffusion lengths if you make a coaxial structure out of it. So that you can minimize the dimension of each to enable efficient absorptions and carrier extractions. For chiral branch structures, a natural application is for optical rotation. You can use the karyotes for that. But people ask what can we use for the dislocations, right? I think for some specific material systems, dislocation can be a good thing. For example, there is an emerging field called the topological insulator. In this case, dislocation is topologically protected, so they're still conductive. This is very good for the thermoelectrics applications, because for the thermoelectric applications, you want to have a high electronic conductivity and lower thermal conductivities. Think about if you can engineer dislocations so that it can efficiently kill the thermal conductivities, at the same time increase the electronic conductivities. That's exactly what you want. So there will be some interesting, and by the way, all these topological insulators happen to be good thermoelectrics materials as a starting point. So there are a lot of things can be done down the road. So summary for the whole talk. The first part of my talk is about switchable thermal rectifiers, self-control thermal devices, so that you can have a lot of applications, for example, for thermal storages. second part of my talk is about the Ohms Law cells for light trappings. Of course, a lot of things need to be done. A lot of understanding need to be done in order to further push the envelopes. I didn't get a chance to talk to you about the thermoelectrics part, but hopefully I've convinced you that when you can control the materials in nanoscales, you can use them to manipulate the flows of phonons, electrons, photons, and to enable new energy devices. Thank you very much.
So for the branched growth, how do you introduce the catalyst particles? You start with the rod.
Yeah.
How do you get them onto the sides of the rod?
Yeah. So lesson is an interesting system. That the lead itself is a catalyst. So it's self-catalyst growth systems. People actually have demonstrated that. So when you fit in a lead sources, it already can nucleate from that and grow these secondary branch structures. So that's what we found out. Yeah.
Do you have any kind of comparison of the nanodome versus amorphous silicon grown on a roughened substrate? So you just have random texturing?
Yeah, so experimentally, 70.5 million per centimeter square is highest achieved in a single junction amorphous silicon cells. So it just based on the result. And short circuit current is directly related to the absorption of that.
How do you define the most ever for any thickness or the most for a given thickness?
I think most for all the thicknesses. Yeah, because I mean there is a sweet spot for the thickness. If you increase that, you increase absorptions, but then you cannot extract electron pairs. So there is a sweet spot. People don't use as thick as possible to do that, right? So, and the highest theoretical value is 20.5, and 70.5 is the highest experimentally achieved. So based on that results, that means it's pretty good. It's better than most of the other things. And people, I think now, the Stanford group are collaborating with some best amorphous silicon facilities. They're trying to do a fair comparison because now the qualities are all the same. They try to do that. But based on the results they got so far, it's the periodic structures is better or higher than the random structures.
So, there are no other questions. Thank you very much. It's very exciting. We appreciate it.
Thank you. Thank you. Timing is exactly right.
Yeah.
You get very good control of it.
Is that your computer?
Yeah, that's my computer. Yes.